Okay, good morning, everybody. Can everybody hear me well? Okay, so yes, welcome to those lectures on flavor physics. Let me just get right into it with some introductory remarks. It will be some very trivial things that I will say at the beginning, just to set up what flavor physics is about. And I guess I will start here in the middle, and then we'll spread out. I guess we'll see how that goes. Okay, so flavor physics and some introductory remarks. As we all know, if you look at the fermion content of the standard model, we have the quarks and the leptons, and they come in three generations. So we have the up quark, the charm quark, the top quark, the down, the strange, the B, and then we have three neutrinos, and we have three charged leptons, the electron, the muon, and the tau. And if you look at those fermions, these different rows that we have here, they are determined, or we can distinguish them by their gauge quantum numbers, how they transform under the gauge symmetries of the standard model. And then the different columns, those correspond to the three generations of the different flavors of quarks and leptons. And what flavor physics is about is trying to understand the different properties of those different flavors and the transitions between the different flavors. So flavor physics studies the properties of the different generations of quarks and leptons. And the transitions between them. And historically, flavor physics had important and significant impact on the development of the standard model. And you've probably heard some of those examples before. Let me give you a few of them. So historically, flavor physics had important impact. And sort of the classical example is the prediction of the charm quark. So measurements of rare kaon decays, in particular the decay of a k long into two muons. The measurement of the decay rate of this process turned out to be much smaller than one would have expected originally. So at a time where only the up quark, the down quark, and the strange quark were known, people were predicting what the decay rate of the k long into mu plus or minus would be, and they found something that is much larger than was actually measured. And that measurement then led to the prediction that there should be this additional quark, the charm quark, which was then able to reconcile the prediction with the experimental measurement. So the decay rate of this process was measured to be much bigger, but much smaller than predicted. Which led to the prediction of the charm quark. Another example that is often quoted is the discovery of CP violation in the kaon sector. That led to the prediction of the third generation of quarks and leptons. And the third example is the observation and the measurement of B-meson oscillations. Oscillations of B-mesons and anti-B-mesons. More precisely, the measurement of the corresponding oscillation frequency. That was used to predict the mass of the top quark. Long before the top quark was actually observed directly at high energy colliders. These are now examples of how flavor physics, how these measurements of flavor processes led to insight into new particles, into new physics at a time that should be out there and that should exist. And the hope is that such a story might continue. Currently, I guess that the main role of flavor physics is in the indirect search for new physics. So the hope is that one will find similar things in precision measurements of flavor observers that don't agree with standard model prediction, that would indicate that something else is out there, some new physics particle that might lead to some unexpected effect, and that then could be predicted to some extent at least. Maybe one gets some indication about a new mass scale that should be out there that would then become the target for direct exploration at future colliders. Yes?
Before these discoveries, did anybody think about or predict that there could be 3 generations, or did the predictions sort of follow from the discoveries?
I'm not sure if there were any speculations about a third generation before that. The discovery of CP violation in kaon sector, if you have only 2 generations, at least in the simple setup of the standard model, you wouldn't get any CP violation. So a third generation in that context would be necessary. There are other ways in principle to explain CP violation in kaon oscillation, so that a third generation was not the only possible explanation at that time, but it was one of them. And I don't know if there were speculations about that before that already. Other questions about that? And please interrupt me anytime with questions, and just shout if I don't see you immediately. Yes. So as I said, in the current era, the role of flavor physics is that as indirect probe of new physics, And the hope is that such a story will continue and that there will be indirect evidence for some new physics that then can later be searched for directly at colliders. Okay, then let me move over here. Let me also give you a very brief overview of the current experimental landscape where measurements, precision measurements in flavor are performed. I hope everybody in this corner can see when I write here. Okay, so there are currently, I would say, two main experiments that are doing precision flavor measurements. And on the one hand, that's the LHCb experiment at the LHC, and the BEL2 experiment at KEK in Japan. LHCb, well, sits at the LHC in a proton-proton collider. So we have a large production cross-section of all kinds of B hadrons, D hadrons, charmed hadrons, and also taus. So what LHCb does is physics of B hadrons, of charmed hadrons, and can also do tau physics. And BEL2 is a dedicated B factory, so it's a E plus E minus collider running at the epsilon 4s resonance, producing BB bar pairs. So they are doing mainly B physics. So either B0 or charged B mesons. But to some extent also charm physics and tau physics. The BEL2 is called a B factory, but actually the number of B hadrons or B quarks that are produced at the LHC is much larger than the one that is produced than those that are produced at BEL2. But the advantage of BEL2 is that it's in a much cleaner environment. So yes.
This might be kind of an obvious question, but what's special about bees? Why are both of these experiments sort of focused on that?
Yes. In the past, we had a lot of measurements in kaon physics. So kaons are known relatively well already. And B physics, B quarks being part of the third generation, an area which is less explored so far. So these experiments are dedicated to do B physics and to study B quarks or B hadrons with high precision, trying to understand if anything funny is going on in the B sector. And also from a theory perspective, maybe because Bs are part of the third generation, maybe third generation is maybe most sensitive to new physics. There are arguments one can make in this direction. So that's another reason why it might be interesting to focus on the B sector. Yes?
Then why not top factories?
Top factories, yes. Yes. One would like to have top factories for sure. The LHC in some sense is a top factory, produces a lot of tops. One would like to study tops as precisely as possible, and one does it at the LHC to some extent. But yeah, because tops are much heavier, the number of tops you produce is much smaller than the number of B quarks or B hadrons that you're producing. So you can study, in that sense, B quarks or B hadrons much more precisely than you can do tops. All right. Now, Bell 2 started data taking fairly recently, a few years ago. And Bell 2 is expected to collect roughly 50 times more data than the old B factories were collecting. So, well, it's Bell 2, so there was also a Bell experiment which stopped running roughly a decade ago. And also Babar, the other B factory. So they produced roughly a billion or so of those B mesons. And Bell 2 will produce something like a factor of 50 more than that. In the case of LHCb, also there one expects much more data to come in the future with the upcoming runs of the LHC, and with the high luminosity runs, LHCb will get something like 30 times more data than what they have so far. So in both of those cases, one can expect a lot of improvement in the precision of many measurements that already exist in the B sector. And on top of that, there are many other experiments that are doing flavor physics measurements, mostly small experiments that focus on specific processes. So one experiment is Na62. That is at CERN. That looks actually at a very rare kaon decay. That is looking for K plus to pi plus neutrino antineutrino. It's a very rare decay. It's a branching ratio at the level of 10 to minus 10 or 10 to minus 11, so it's extremely unlikely that a kaon decays in that way. And it's also very difficult to detect because of these two neutrinos. So far, this decay has not been observed. They're starting to have evidence for this decay, but it's an interesting process and in principle, an interesting probe of new physics. And the goal of Na62 is to measure that with pretty high precision at the standard model rate. Yes?
Why this process of all the rare processes that you can measure?
Oh, say it again, sorry.
Yeah, why this specific process of all like the rare processes?
Oh, yes. Well, this is one of them that hasn't been measured yet. So there have been measurements of other kaon decays, which are also rare and which are sensitive to new physics. That guy, for example. But that one, because it is very difficult experimentally, hasn't been observed so far. Though it is conceivable that there is maybe new physics hiding in that one. And so sort of in the spirit that one should know, you don't leave any stone unturned. You sort of try to go through all the various processes and try to see if you can measure them with high precision and compare them to precise standard model predictions to see if there might be some new physics showing up. The other thing about this decay is that it is pretty clean theoretically. You can predict it with pretty high precision in the standard model. And that's not always the case for those flavor processes. In some cases, there are large uncertainties that one has to take into account. But in that case, this K2 pi nano bar is particularly clean theoretically and can be predicted with high precision. And so you want to measure it also with high precision. And this Na62 experiment is designed to do exactly that. There is another experiment that looks for rare kaon decays, which is called COTO. That looks for the corresponding neutral version of the decay, a k long to a pi 0 neutrino antineutrino. That's an even more difficult measurement because now you have all neutral final state. Pi 0 is much more difficult to detect than a pi plus, and you also have less information about the initial state because it's also neutral. But also in that case, COTO is, at least the expectation is that eventually they will be able to measure this process at the standard model rate, and will discover that process. There are various experiments that also look for flavor transitions in the lepton sector. The MAC2 experiment, for example, that will be looking for mu2 E gamma, so a flavor changing process in the lepton sector, or the mu2E experiment that is looking for mu2E conversion in nuclei. And there are various other experiments which make precision searches for processes that are extremely rare or absent in the standard model, or precision measurements of things that do exist in the standard model but have very suppressed rates. So after this very brief intro, let me now give you a sort of outline what I want to do in these 4 lectures. So we just did the intro, then the actual introduction, I guess, will be coming next. So the section I call Flavor in the Standard Model and Beyond. And I will just try to lay out the basic language that we use in the context of flavor physics, basic principles, lay the foundation for the other things that will come subsequently. And we'll spend quite a bit of time on that. So, all of today and probably also most of tomorrow, we will be spending with that chapter. And then I will go into more details, so specific aspects, and discuss them in more detail. One thing that we will be discussing is the determination of the standard model flavor parameters. As you probably know, in the context of the standard model, all flavor violation is governed by the CKM matrix, which describes the mixing between the quarks in the standard model. And we will discuss to some extent how these CKM matrix elements are determined, what we know about them. We'll talk a bit about the various masses of the quarks and leptons in the standard model, that there is a weird hierarchical pattern in those masses and also in the CKM matrix elements. And that will lead us then to the next part, which is the so-called standard model flavor puzzle. So this is the question of why are these hierarchical patterns among those flavor parameters. The standard model flavor puzzle. And we will at least sketch a few ideas that people came up with to address those hierarchical patterns that are observed. And then at the end, I will talk about the case of B mesons and the so-called B anomalies. So that's a topic that led quite to some excitement in recent years. So there are a set of measurements from LHCb mainly that don't agree very well with standard model expectations. So the hope again would be that maybe it is some indication that some new physics is out there, and this might be some indication that there is some new physics, and I will discuss that to some extent at the end. There are many other topics one could talk about in the context of flavor, but we only have 4 lectures, so that's the choice that I made. Any questions before we get into that? All right. Then let's start with flavor in the standard model. And beyond. And now let's get back to this chart that I'd drawn before, the various quarks and leptons in the standard model. Let's now be a bit more specific and precise, and let's remind ourselves how those various particles behave under gauge interactions. So we have 5 different matter fields to consider. These would be the left-handed quark doublets, would be triplets under SU3, doublets under SU2, and hypercharge 1/6. So those are the standard model fermions with their quantum numbers. And I put here index J, that would be the generation index going from 1, 2, and 3. In addition to the left-handed quark doublets, we have right-handed up quark singlets, triplet under SU3, singlets under SU2, hypercharge 2/3. Then we have the right-handed down quarks, 3, 1, minus 1/3. Then we have the left-handed lepton doublets, which contain the left-handed charged leptons and the neutrinos. 1, 2, minus 1/2. And finally, the right-handed charged leptons, 1, 1, and minus 1. And in the context of the standard model, when you write down the Lagrangian, we will have kinetic terms for all of those fermion fields. So let me do the following notation. I will denote all of those fermion fields with psi. So psi runs over those 5 different matter fields, the Q, U, D, F, E. And then I will also write explicitly a sum over the flavors. And then we have a psi bar covariant derivative psi. So the first one is a sum over these different fermion types, and the second sum would be a sum over the different flavors within each type. And these kinetic terms, they respect a large global flavor symmetry. Let me call that G flavor, and that's a U3 to the 5th symmetry. So these are individual U3 transformations on each of the fermion types. You can just, yes?
Is there a simple way of seeing why it's to the 5th?
Yes, this corresponds to these 5 different meta representations. So I can do a U3 transformation on the Q type fields. Can do the same thing on the U types, the D types, the Ls, and the Es. So these are individual U3 transformations. For Q, U, D, L, and E. And these kinetic terms, they are completely invariant under those global U3 transformations. What one often does then is to decompose that flavor symmetry into SU3 factors and U1 factors. And let me write it now explicitly. There will be a SU3 for the Q fields, an SU3 for the U fields, SU3 for the down fields, SU3 for the left-handed leptons, SU3 for the right-handed charged leptons, and a U1 to the 5th symmetry. And so all these SU3 transformations, they correspond to the non-trivial flavor mixing. And then on top of that, we have these 5 U1 factors, which don't transform the different flavors into each other. But those include, for example, things like baryon number and lepton number. Yes?
Why does the U1 need to be included in the large flavor group?
We don't, I mean, it is a symmetry of the Lagrangian, so you can include it. Most of the time we will talk about these SU3 transformations because we're mainly interested in the actual non-trivial flavor transformations that switch from one flavor to another. But in principle, it is there, and one can include it. And it will play some role when we start counting parameters. What are the actual physical number of parameters that are there in the flavor sector? Then it's useful to keep those U1s and keep track of them, how many of them remain once one breaks flavor symmetries. Okay, so that's the kinetic terms of the standard model Lagrangian. Of course, these are not the only ones that involve fermions. The other part that is relevant for the fermions are the Yukawa couplings of the fermions to the Higgs. And those Yukawa couplings, they will break this flavor symmetry. So let me write out how the corresponding terms in the Lagrangian look like. Now we have again a sum over flavor indices. Now two of them, J and K, and then there are Yukawa couplings for the up-type quarks, YU, and in general this will be 3 times 3 matrices in flavor space. So they have this flavor index J and K. And the corresponding operator would be a QJ bar, a UK, and then the conjugate of the Higgs field, plus Yukawa couplings for the down-type quarks, again with flavor index JK. Now a QJ, DK, and the Higgs, and then the same for the charged leptons. With a LJ and a EK. And a plus Hermitian conjugate to make the Lagrangian Hermitian. And that's in a convention where the hypercharge of the Higgs is plus 1/2. And these are the gauge invariant terms that one can build out of the fermions and the Higgs at dimension 4. And as I said, these Yukawa couplings that show up here, this YU, YD, YE, they are in principle complex 3 times 3 matrices. So 3 times 3 matrices in flavor space. And that part of the standard model Lagrangian is not anymore invariant under this flavor symmetry. It breaks this flavor symmetry almost completely up to a few U1 factors. And what comes next is something that you're probably familiar with, so I don't want to go through that in all details. Want to expand the Higgs around its vacuum expectation value. The terms with the vacuum expectation value combined with the Yukawa couplings to give mass matrices for the quarks and the leptons. Again, they are still generically 3 times 3 matrices, and then one needs to diagonalize those matrices to end up with mass eigenstates of the quarks and the leptons. let me just sketch these next steps. One replaces the Higgs with its vacuum expectation value, and then the Yukawa couplings give fermion mass matrices. One can diagonalize these mass matrices by unitary transformations. And then the masses of the quarks and leptons, they correspond to the eigenvalues of those mass matrices. And the remnant of these biunitary transformations is the CKM matrix, which shows up in the charge current interactions of the quarks. So if we go back now to the kinetic terms, and if you perform these biunitary transformations on the quarks and lepton fields, for most terms, they just drop out because these are unitary transformations, and both fields or the same fields show up on the left and the right side of this expression. But for the charge current interactions of up quarks and down quarks with the W boson, there you're left with the CKM matrix. So here you have a weak gauge coupling, CKM matrix, and now a left-handed up quark field. And the left-handed down quark field, and those interact with charged W bosons. So this V here, that's the CKM matrix. And this U and the D in this notation, this would be the mass eigenstates of the up quarks and down quarks. All the other interactions in the standard model remain flavor conserving. So all the interactions of gluons, photons, the Z boson, also of the Higgs, they remain flavor conserving. due to the unitarity of those rotations that one performs on the quarks and leptons. So all the neutral current interactions. So the interaction of photons, gluons, the interaction of the Z and of the Higgs. They remain flavor diagonal. Or more precisely, in the case of photons, gluons, and the Z, they're even flavor universal. And in the Higgs, they are proportional to the corresponding fermion masses. So one says that there are CNCs, so no flavor changing neutral currents. At tree level in the standard model. Yes?
Are neutrino oscillations kind of outside the realm of flavor physics?
No, not necessarily. I guess they're outside the realm, strictly speaking, of the standard model,
Sure.
where we only talk about the generalizable interactions of the left-handed lepton fields. Their neutrinos are massless at that point, so at that point there are no neutrino oscillations. But yeah, we know that neutrinos do have mass and they do oscillate. Yeah, so that would be part of flavor physics as well. I won't talk much about that, but the formalism will be similar to some extent to what we will discuss mainly in the context of quarks. Yes, and this absence of flavor-changing neutral currents at tree level, that is sometimes referred to as the Jim mechanism. Named after Glashow, Iliopoulos, and Mayani. And it basically boils down to the fact that there are these three full generations, and one can have these unitary transformations among the various generations of quarks and leptons. Flavor change neutral currents, even though they are absent at the tree level in the standard model, they do arise at the loop level. And I want to give you an example of how that looks like. Oh, probably. Yes, but then I covered that, so let me jump over there again. And one example I want to give is the decay of a B sub S meson into a pair of muons. That's what's sometimes referred to as a delta F equals 1 process. Yes?
I don't know my meson super well. What is a B sub S?
Good, yes. So B sub S is an anti-B quark and a strange quark. And then the B sub S bar would be the B quark and the anti-strange quark. And this delta F equals 1, that refers to, well, that in this case, the B flavor changes by 1 unit into a strange. So if you draw a diagram, a possible Feynman diagram of how such a process looks like, so we start out with our B sub S meson, which is a bound state of, as I said before, an anti-B quark and a strange quark. And we need to go to a mu plus mu minus pair. One way to do that would be the following. We have here an intermediate quark, which can either be a top quark, a charm quark, or an up quark. And then 2 W bosons, which give a Z boson which then gives the mu plus mu minus pair. And there are several other diagrams that you can draw. That's known as a so-called penguin diagram. There are also box diagrams, which will have a box-like shape. And we can estimate of how big the amplitude for such a process actually is. We won't do the actual loop calculation. That would take way too long, but so that we can estimate of what the result should be. So the generic structure of the corresponding amplitude well, it's a process that goes through the weak interactions. So we can expect that the Fermi constant will show up. We also see that it goes through a loop. That means we will have a loop factor, a coupling squared over 16 pi squared. And then we will have a sum over those different types of up-type quarks that can run in that loop. And each of those contributions will come with its own combination of CKM matrix elements from those interactions of the W boson. There will be a VIS star and a VIB from those 2 vertices. And then there will be a function, a loop function, which depends on a variable that I call xi, which will be the ratio of the masses of the particles that run in that loop, so the up-type quark masses and the W boson mass. And yeah, we could in principle figure out what the function, but then we would need really to systematically look at all possible diagrams that there, calculate all of them, add them up consistently. And it's not really relevant for the argument that I want to make what that function actually is precisely. Yes?
What about
Propagator
propagated for the vector as well?
for the?
What is that?
Oh, yes. That's essentially the Fermi constant. What you do here, maybe I should have been a bit more explicit. So what we do here is when we look at this process, we will neglect the momentum of the propagator of the Z boson, and just approximate that by 1 over the mass of the Z boson, and then just redefining it with some prefactors, we get the Fermi constant. Good. Yes. And we can do that because the momentum which goes along the Z propagator, that will be corresponding to the mass of the Bizabès meson, which is much smaller than the mass of the Z boson. So this condition goes into the derivation of that expression. What I want to do next is now to explicitly look at this sum over those 3 internal up quarks. So what we have here is a sum of the following type. So we will have a VTS star VTB f of xt, and then the charm contribution and the up contribution and now we can make use of the unitarity of the CKM matrix. That means we can rewrite this as a VTS star VTB of times f of xt. And then I want to rewrite this VCS star times VCB as minus VTS star VTB minus VOS star VUB. So I'm using the following which simply follows from the unitarity of the CKM matrix. And then I can rewrite this as follows. And then a second term, which has the VOS star VUB. Yes?
Is there some reason that taking out the charm piece makes the math easier or something, or is it just a kind of a random choice?
Good, yes. It is not completely random. The argument I want to make here is that we will come to that right now. That second piece that shows up here, that is very, very small and can be neglected. So in that sense, what is then relevant is this combination which comes with the VTS and VTB. It's a top quark contribution in some sense, which is the dominant one in the context of this BDK. yeah, so as I said, what enters here is this xc and xu, these ratios of the charm mass squared over the W mass squared, or the up quark mass squared over the W mass squared. Those are very, very small. They are the good approximation. They are just 0. Which means in particular that this last term here drops out, well, because first of all, these two functions, they almost cancel each other. And at the same time, also this VUS times VUB CCAM combination here, that turns out to be much, much smaller than VTS times VTB. So for both of those reasons, this second term is very, very small compared to the first one. So it's a good approximation. We just get a VTS star VTB, and then a f of xt minus f of 0. So there's a cancellation to some extent happening, still at the loop level, but this cancellation is not exact as it was at tree level. At tree level, you don't get any flavor change neutral currents because of the unitarity of the CKM matrix. Here you still get sort of a partial cancellation. However, because the top quark is much, much heavier than the charm and the up, you're left over with some finite contribution at the loop level. If all up-type quarks had the same mass, then the cancellation would still go through also at the loop level. So in that, there's a Jim breaking by the large top mass. And in the case of these flavor change neutral currents, which involves the B quark, then it's typically the contribution from the top quark, which is the dominant one. Yes?
Wouldn't there still be Jim breaking even if the top mass weren't large, just like a smaller amount of breaking?
Yes, I mean, as long as the different masses are equal, you have Jim breaking, and you will have a non-zero flavor change neutral current. But because we know that the top mass is much, much heavier than the other up-type quarks, there's a large Jim breaking if you want, and you get pretty sizable flavor change neutral currents in the down quark sector. One could go through an analogous example for flavor change neutral currents in the up sector. Yes?
Does that term give any suppression from the CKM matrix?
Say it again, this term?
Yeah, is that term much smaller than the first term?
Yes, yes.
I mean, from the CKM matrix.
Yes. There are two reasons. First one is the CKM matrix. This combination of CKM matrix elements is indeed much smaller than this combination. And also, there's a large cancellation showing up here because those XU and XC are both very, very small. So there's another cancellation happening here. So both of those reasons make this second term here much, much smaller than the first term. Yeah, as I was saying before, if one goes through a similar example in the context of flavor change currents for up-type quarks, then one gets a much stronger Jim cancellation because the masses of the down quarks are sort of more similar to each other. Both the down quark mass, the strange quark mass, and the bottom quark mass are all much, much smaller than the W mass. So this Jim cancellation is much more severe for flavor change neutral currents in the up sector. I wanted to give another. How long are we going in time? Is it quarter past or 10 minutes still? Okay. Let me see. Should I do this second example very quickly, maybe? So the second example would be meson-antimeson mixing, or in the example here, B0 bar mixing, which is sometimes referred to as a delta F equals 2 process. So here we have a flavor change by 2 units. We go from a B quark to an anti-B quark, so that corresponds to a change of 2 units in flavor. And again, an example diagram. A B0 meson now would be a bound state of a anti-B quark and a down quark. And there we have these box-type diagrams that can lead to an oscillation into a B0 bar, which would be a bound state of a anti-D quark and a B quark. And again, on these quark lines, we can have all 3 generations of up-type quarks. Yes?
Is it delta F equals 2 because you're going from third to first generation?
No. This corresponds. This refers to how many units of B flavor are removed or created. So here you go from something that has well, I guess this would be a B bar. So you go from an anti-B quark, which has sort of bottom number -1, let's say, to a B quark, which is bottom number +1. So that this delta F would be 2 in that case. But in that case, in this example, you go from an anti-B quark, which is bottom number -1, to a strange quark, which has bottom number 0. So that would be a delta F equals 1 process. And again, there are a bunch of other diagrams that we would need to consider. In that case, this CKM structure is a bit more involved. So the corresponding amplitude, that would be now a sum over 2 of those up quark indices. The VI D star, VIB, and a VJD star, VJB, times a loop function which depends now on 2 mass ratios, xi and xj. And again, in this example of a process involving B mesons, if you work out the conditions that you get from CKM unitarity and do the corresponding replacements and neglect small terms, you end up with an expression that looks as follows. You have a VTD star VTB squared times something that only depends on the top quark mass, fxt plus a f00 minus 2 times fxt0. That's the leading term that is left over once you take into account CKM unitarity. Yes?
You mentioned earlier that people expected the top quark mass from this
Yes.
process. Is it just like you measure this and then you
Basically, yes, exactly that. Yeah, yeah.
How exact was this?
Not very exact, not very exact, but it indicated that the top is much heavier than the other quarks. So that came out from those measurements. But in principle, one could do it very exact. I think with nowadays calculations of those processes, and if you take the known oscillation frequency of B mesons and use sort of the state-of-the-art standard model calculation, you would be able to get the top quark mass fairly precisely, actually. Yes?
When we do that, what mass are we actually calculating? Is it like the running mass at some scale?
Good, yes. I mean, it depends how you do the standard model calculation. The standard choice would be that you use the MS bar mass at whatever scale you choose, typically the scale of top quark mass itself, or maybe the W mass or something like that. But yeah, so those calculations are typically done in the context of an MS bar renormalization scheme. Okay, so those were some basic properties of these flavor-changing little current processes. The next thing I want to do is talk a bit about parameter counting and coming back again to these flavor symmetries that we had at the beginning. But I think we're almost out of time, so probably doesn't make sense to start that. So any questions about this stuff? Yes.
General question, I guess, how are we defining a flavor-changing neutral current? I mean, I see charge currents running in this loop, so
Yes.
I wouldn't call it that.
Yes, so I guess the overall process, you have I guess you could formulate this process in terms of four fermion interactions where you have a B quark, a anti-B, a down, a anti-down, and a B as external states. And there you don't have any change of charge in that process. In that sense, it's a flavor-changing current process as a whole. But you're right. Internally, it's all charge current interactions, at least in the context of the standard model. If you go beyond the standard model, such a process of B0 bar oscillations doesn't necessarily have to go through charge current interactions. There could be some new physics that directly connects, for example, a B quark with a down quark through some interaction. And then you would have this flavor-changing current process induced by flavor-changing neutral currents at the Lagrangian level.
And one other one, on this NE62,
Yes.
you wrote down just the positive charge kaons. I wonder why.
Oh, it means both. I actually don't know the experiment itself. I think it might be only running with one particular charge, but in principle, you can also do it with negatively charged kaons. There's nothing specific to positively charged kaons in this process.
Is there to the experiment, though?
In the experiment, I actually don't know if they use positively or negatively charged kaons. It might be that experimentally one of them is preferred, but I actually don't know. Any other questions? All right, then we will continue tomorrow.
Positively charged kaons, they run, I think, some very particular beam line down a different member.
Yeah.
So that's where the preferential selection comes from. Because the source they're actually using is preferential to positive. Yeah, so you can very much tune it to the other way around.
Is it an electron dump? Is it an electron dump?
They do have to still like hit a material and create the cannon.
But do you know what the beam is?
Yes, I guess it's a proton
Oh, it's proton.
beam, I believe. Yeah.
Okay, so maybe, okay.
Yeah.
You said it was positive?
Yeah.
Gotcha.
Yeah, it's 400 GeV proton B.
I see. I think something better gas or something.
There's a name for it. It's no, I guess it's just primary beam. Yeah, I don't recognize no further than that.
I
Yes,
just wanted to thank
sure.
you for answering all my questions. I
Oh,
know
of
I
course,
ask a
of
lot of
course.
them, so I really
No,
appreciate
no, that's good.
it.
That's
I don't
good.
really
Great.
know too much about flavor physics, so
Yes,
I've been looking
yes.
forward to these lectures.
Oh, sure, sure.
Thank you.
Yes, of
And
course.
I'm Anne Catherine, by the way.
Oh, nice to meet you.
Nice to meet you.
Can I ask you a question
Sure.
about the meson mixing? It's
Yes.
actually not in this lecture. It's something I never understood. So
Okay.
maybe you can help.
Yes.
So when I was learning about K-on mixing and K-long and K-short, I saw that you can use the oscillations to measure the mass difference between
Yes.
them. But then when I look at the PDG, it also tells you which one is heavier, K-long or K-short. And I never know
Yes.
how people know which one is the heavier when all they can measure is the mass difference.
Good. Good question. Yes. Yes.
I asked this question, finally didn't let you, so I'm sorry to put you on the spot. It's just still
Yes.
bugging me.
Yes. No. That's a very good question. Yeah. So the oscillation frequency, there, I guess measuring that by itself would be
Only tells you the
difficult to.
difference in mass,
Yes,
right?
exactly. And so, how do you know the ordering of the masses? Is the question.
Because it looks like people know, and I was wondering, is that something they can predict theoretically, or is it just something we measure experimentally? Or
You can certainly predict it,
okay,
but
because I tried to find it in the internet and I couldn't.
yes, yeah. I mean, if you do the calculation in the standard model, you will get the sign of that mass difference.
Okay. Do you know a reference where they actually do the calculation? Because I tried to find it and I couldn't, so I began to wonder if it was just something people measured experimentally.
I don't know exactly how that would be measured experimentally. It might be possible somehow, but I don't know now how that would work. But I'm pretty sure one can calculate it in the standard model, and maybe it is just this assumption that it works out as in the standard model, and this mass difference has that sign, or maybe there's more behind it. I will try to look that up, and I will send you some references. Yeah.
I had a quick question about these the loop functions.
Yes.
In particular, how should I expect them to behave as one of the masses goes to zero? Like in the limit where one of the x's goes to zero.
Oh, yes.
Is there some behavior that?
Yes. Those functions, if one of the if both of those x's go to zero, then you will have some constant that you will have, and if only one of them goes to zero. Actually, not sure now what exactly you would expect. It's not. It will have still some dependence on xt, but I guess it could still contain a constant term. Yeah, what essentially happens in this particular combination, all the constant terms they drop out, and if you would Taylor expand it in xt, you would start with xt as a leading term.
And just to make sure I understand, these f is symmetric in.
Yes. Sure. Hey. Sure.
Two questions.
Yes.
One is, so we say that this is a CP validating process, but I can't say what it has to do with the CP validating phase in the CKM matrix.
Oh, I mean, yes, you're right. I mean, the amplitude for this process is proportional to this CKM matrix combination, and that will have some complex phase.
Yeah, but suppose we don't have the CP validating phase.
Yes.
And then this Lagrangian is CP conserving, but this still it seems not to be zero.
That's true. I mean, the oscillations themselves happen. The oscillations themselves don't indicate CP violation. Meson oscillations, they happen also without CP violation.
So B to B bar mixing is not CP validating process by itself?
But not by itself, no. I mean, there are CP asymmetries in the oscillation. So there's a difference in B0 going to B0 bar and B bar going to B0. And that difference, that's a sign of CP violation. It's the same thing in kaons. Kaons can also oscillate without CP violation. That's perfectly fine. But there's a difference between K0 to K0 bar and K0 bar to K0. And that difference signals the p-violation, and that is proportional to phases in the CKM matrix.
You can sort of solve both of those problems.
So that means is that because from B0 to B0 bar is the conjugate of
So
B bar?
Yes,
I actually was just
yes.
back in the of our papers, and I can show you the
Another question is, suppose that all the fermions have the same mass.
Yes.
Will this be completely forbidden at all?